Group, please hear me. Hello? Hello?
Yes, sir.
You can see the screen, right? Hello?
Yes, sir.
I talked about clusters. Here, I have given you the mind, last node and compactness, net characterization of compactness and taken of products. Theorem 1, I have avoided subnet. Right now you can avoid subnet. Theorem 1, what I am saying, you have a topological space and you have following a requirement. One thing is following a requirement A, extra is compact, and then property B, every family of closed sets, closed sets in X having FIP, finite intersection. You see, from the definition of finite intersection property, empty set cannot belong to that family, has non-empty intersection. Every net in X has a cluster. For the cluster definition of cluster, what you don't need to subnet, so that I can avoid talking about subnet. In fact, there is a famous topologist. He has a book, Angel Key, Giant Topology, big book. It's a encyclopedia. He doesn't talk about subnet. He deals everything with in terms of cluster. Now here, I would like to mention that you should read the book. Usually in books, in elementary books, you will see that. This is very straightforward. Okay, this is very straightforward. So that here I am adding this, so that I have gone to B implies C and C implies A. In fact, yesterday I gave proof of this basically. A implies B. it is written again here. So B implies C. So look at that. You want to prove that every net has a cluster point. So you are starting with a net, but you want to use B, so you need a closed set. That's why for each lambda I have taken this. X mu, actually mu greater than or equal to lambda. But I told you usually in the net they take this relation. Okay, but by this we mean this. Actually, you could say that why we didn't take this relation. We could take that. So f lambda, so you are taking, I am taking the closure of this. Okay, that's because I have closed sets. So that is the idea that why we are taking this. And then easy to see that if you have this, then the other. Okay. Now easy to see that since you have this, because of this thing, you can prove that. Look, here I am using the property of the net, that if you have this 1 I, 1 to n and that, lambda 1, lambda 2 basically. If you have this lambda 2, lambda n, remember that a net directed set has one property. That is important property, directed set. That if you have lambda 1, lambda 2 in the directed set, then there exists lambda 3. Such that you have this lambda 3 greater than or equal to lambda 1 and lambda 3 greater than or equal to lambda 2. So here you want to show that it satisfies finite intersection property. So that lambda 1, lambda 2, if you have it, so by induction, if you have 2, then for 3 you can have this. So for n, I have 1 lambda such that okay, and then by this property, I will have this for each I, so that particularly it will be this. This is non-empty, so this will be non-empty. That means all this collection has finite intersection property. That means this is first of all closed sets that I have taken closer. Let's do that. I have taken closer. Okay, so closed sets. So it has FIP. Okay, right now. Condition B says that if you have a collection of closed sets with FIP, then intersection is non-empty. That means I will have this thing. Okay, and now by using that, you can easily prove that it will have a cluster point. That I said x lambda clusters at x, because if it is non-empty, so you take any x. In fact, it will cluster any point here. That means it may have more than, if the intersection has more than 1 point, so net will cluster at more than 1. But we are only need to prove that it has a cluster. Okay, so that take an intersection here, same way you do it for sequence actually, so that you show that it clusters. That I have proved. Okay, right. So this is done, and C implies A. Here again, that if you do not have compactness, means what? That is a very vital thing. You should understand. If it is not compact, there is negation. That means you'll have an open cover of this. That means there exists, if you have this, there exists an open cover of X without any finite subcover. Without. negation of the compactness without any finite subcover of this technique you need to learn. That means whenever you take U1, U2, UN, finite collection here from that, okay, that won't cover this. That means union UI, I1 to N won't cover X, not equal to X, right? That means X minus this will be non-empty. But exactly I've taken GI instead of U or G, so it is this thing. Okay. Now, what do we have? I'm taking that. Let F be the family of set of all non-empty finite subfamily. Can use family also. I don't know why I crossed it. F is equal to what? Non-empty finite subfamily. That means here you take any finite subfamily and take the collection of all these possible finite subfamilies. Okay, that means it is a, if you look for the power set of this, that means you are taking not the whole power set, you are taking only finite subsets of this. So basically you can take F will be actually something like this. U prime is this, D prime is finite. Okay, taking all those the finite subfamilies. Finite, this is very important. Okay, because I'm going to use this thing. Okay, so that I have used that. Okay, so after that proof is easy, it's still difficult, but you read the proof. I'm not going to read the proof of this. Okay, so that, but I told you the idea of that. That since I'll have to use this, so I am taking this family. Okay, so that here look U lambda. So that means basically, well, this basically this will be a directed set. How do I make it directed set? This will be directed set. How I am going to put this is directed set. Okay, here I am giving this. Okay, to straight you can take that U1 for U1 U2 belongs to F to 5. If well, let me tell you that I'm not very sure. You should check whether it is straight, it is inclusion, set inclusion. Sometimes, like neighborhood filters, they've taken that. The reverse set inclusion. You reverse it. So that when you take such a relation, be careful that whether you are taking the appropriate one, this one or this one, which will work. Okay. So I have taken this one. Let me see that this works. Okay. First of all, this I already said that, and there exists actually this x lambda I am calling u lambda. Given this u lambda, the finite family, this is very important. This is non-empty, so that some elements belongs here. That because of this u lambda, I am calling it x lambda. Okay, and this way I am getting a net. Given u lambda, I am getting x lambda. X lambda is a net, and I show that this net doesn't have a cluster. Okay, that exactly. We claim that x lambda doesn't have a cluster. Okay, that's the idea. That how will you pick up a net without a cluster point? That violates C, and that you can see the proof. Okay, that only 3-4 lines are left. Okay. The trick is that you see that I have given u1 u2 u1 greater than equal to u. I am using the definition of cluster point, and then first element I am adding here u. Okay, and then u1 u2. Okay, there exists anything in that. Because there is a finite family. On that finite family, you take u and some other members whenever you have that. Okay, and then it is not satisfied. So that X lambda doesn't have a cluster point. Right. So that here I would like to point out that if you go for Wheeler, because I am going to give the proof of the Tychonoff product theorem, and that I will explain that. But Wheeler, here see characterization of compactness. The first theorem in chapter 17. He has given a lot of characterization, including he has used, I'm telling you, filter. Corresponding coming is ultra filter. Add net, ultra net. I have not taught you filter, ultra filter. Filter. It would have taken another 2 lectures minimum there. That's why I am avoiding that. Actually, some people only discuss filter, they prefer, than net. Some people take only net. But actually it will be more convenient if we can discuss both filter and net. And Willard has done that. That's why he could give the entire characterization of compactness in terms of both filter and net, because then he can use it to give a simple proof of the Tychonoff product theory, which I will explain now. And he also, after the proof of Tychonoff's product theorem, he made a big comments and like that. The Tychonoff didn't have advantage of all these tools, so that's why his proof was not that simple. Though Wheeler's proof looks simple, but before that he has done a lot of things. Filter, net. By the way, I'd like to mention that Wheeler did PhD under M.H. Stowe. I think H. Stowe. Other one. But I told you he was a British. But Sage, because Wheeler did PhD, it was a good department once in mathematics. University of Rochester. Right now, I don't think the mathematics department is that strong, but 60s, 70s, it was a very strong mathematics department. But H. Stone did PhD in Princeton University, so he was a British. So actually, he worked here also, but he worked, I think later on he returned to the UK. So he taught in British University. His wife was Dorothy Ara. After marriage, she used to add this Dorothy Maran's too. But yeah, don't make any mistake. She herself was a good mathematician, major theorist. She also worked in University of Rochester, major theorist. Dorothy Maran. So she was also very well reputed mathematician. There, another couple that you have, Walter Rudin. He was basically an analyst, but he is more well known about his books. His wife was a very Ellen Rudin. They both worked in University of This is a good department. It has a good department in mathematics. Wisconsin, Madison. Its computer science department is also good. Mary Ellen Rudin was a set theoretic topologist. Talking about math, but as a researcher, he was far more reputed than her husband. She was a tariff figure in this topic. In fact, to encourage the young topologists, there is a, I think, American Mathematical Society has an award, Mary Ellen Award, Mary Ellen Rudin Award. Right. So I'm just talking about some history, so that you can do that, so that I can make sure that C implies A. You understand the proof. I may not give the whole theorem to prove, but I may give, because it will be offline exam, in class exam. I may give C implies A to see that you have understood that. The two things. Definition of cluster point of a net and how to use this negation of compactness. Okay, so that you should read the proof carefully. Okay, I do not think you will have difficulty in understanding. Now the next thing what I do it, is that look, when I have finitely many topological spaces, what I want to explain. Then I have taken the product of this and this I define product. How I define this product that is related to each of them. Basically, I have taken all these things. Ui belongs to tau I. At this satisfies the condition of a base for a topology. So it gives a base. It is a base for a topology on, call it X, product on X. That was called the product topology. Okay, right? Product topology. Look here, I do not need any axiom of choice. I know if I have finitely many non-empty sets, there it will be non-empty. Because if it is non-empty, then x1 is here, like xn is here, so that will be here. For finite family, you don't need axiom of choice. Okay, right? Now suppose I have an arbitrary family, x of tau y, arbitrary family. This is that means particularly suppose it is infinite, maybe large in infinite. Then first of all, I know by axiom of choice if each of them is non-empty and this is non-empty, of course I am taking non-empty. If each xi is non-empty for let me write this. This is what I am saying. If non-empty family I not equal to phi and xi non-empty for all I, for each I, then this is product is non-empty. That is actually axiom of choice. Actually, axiom of choice. Okay. I am talking about first this collection, and then I will come to this defining a topology such a way that when you take I to be finite, because it is general thing, then it will be the same thing. Okay. Now look here, how first we recall that, how we define this thing, how it is defined. But remember, this is actually a collection of all functions from I to union xi. I belongs to I such that a phi belongs to xi for all I. This was the condition. So such a thing is called a choice function. The choice function. So that axiom of choice is equivalent to the existence of a choice function. Okay, choice function. If you have such a function, then obviously it will be non-empty. Okay, so usually Fi you denote by xi, and if this is a function we list by its elements. If I write this way, that will tell you the whole function. So usually instead of F5, I write xi to indicate it is coming from xi. Sometimes, if there is no confusion, we simply write this xi like net. But don't confuse with net. This is an element of this product space. This is product space. Okay, right? Now look, so that product was defined this way, and the projection, kth projection, pi k, some people call it pk notation, they use pk. Projection like that, like finite thing you have done it, that xk. That means here if you have a point like this, okay, it is going to the xk. That means we call it kth coordinate. Here, this is called the ith coordinate of the point. Like Euclidean space, Rn you do it, ith coordinate. So it goes to the kth coordinate. Projections means you project the point on its kth coordinate, then this is called the kth projection. So this is pi k. Okay. These product space, when I want to define product topology, these are the important. They play a big role. In fact, you can handle these things, you can handle the product topology. Now look here, so that I have given some justification that in order to give the how we define product topology, it is better if we have the idea of the subbase. Okay, how we are defining subbase. Okay, so that so in order to define the product topology in terms of that, we want to define the product topology on this product in terms of this projection maps. Here I have taken special thing, that's a key by key. So this is this projection maps. In order to do this, in finite case it is worked based, but actually I need to talk about subbase. What it means subbase? That I have given the definition, that definition 1, page 3. Okay, page 3. That look, here I am saying, suppose you have a set X, okay, and A is a family of sets, some set, not all, okay, some subsets, non-empty family of subsets of X. Actually, I can't write that way because this will mean all subsets of a power set of X. So actually, it will be better if I write this way. Subset such that what I have put the condition that X is coming this. And all the members of the union of all the members of S gives you X. Okay, gives you X. That's the condition I put. And then how I will say it, why I call it subbase. Because from this, if I have this condition, from this I want to have a base. Okay. And here I said that SBS subbase and B consists of all finite intersection. That means you take this thing. All these types, but this is not fixed. So that basically you take a finite subfamily of this, take its intersections, all such possible finite intersections. Okay, that exactly. That consists of all finite intersections of sets of the form. Then you can check that if I do it, then you check that B is a base for a topology. That you will have to think that whether a collection gives you a base for a topology and adds a topology rather, then you need two conditions that you can check that is a base for a topology on X. Okay. So that's why it is called subbase. It need not be base. But if I take all the finite intersections of this, that will give a base. Okay. Right. And B is called the base generated by this, and tau is called the topology generated by this. Now the thing is, so this is subbase definition is very simple. Okay, but I am only putting this condition. But let me tell you that since I am taking finite intersection, it's a result of logic actually. So if you consider empty intersection, not empty intersection means not the intersection over empty family. Over empty family, this means finite family, no member. Intersection over empty family. Now look, if you take intersection over family, if it family becomes smaller, over which you are taking the intersection, then your resulting set will be bigger. Like here, let me explain. Suppose you have a set X and you have this. Now suppose you have this. Then what will happen? If I take this, this is intersection for a smaller family, and this is intersection for a bigger family. But then you can easily check that it will happen, right? Because you have entire thing is here, and probably more you have. But if you, by intersection you will go for a smaller land for a smaller set. But union is the reverse, bigger set. So if you have it, then this is the run of the logic here. An empty family can be the smallest family. So this will be give you what? That means if I take this empty family, suppose now, so if you take this empty family, suppose the family, this, but this is empty family, there is no member, so it should give you the whole thing X. That's the logic that is consistent with our other assumptions. So if you take intersection over empty family, then that will give you X. That is the reason some people don't put this condition, because ultimately I am taking intersection over a finite family, But if you allow empty family, X will be automatically in a member of the base. Look here, X is a member of this by my definition. And S, don't forget, S is a subset of this because you take single member. So that will be also in B. Okay. But if I don't allow it, then X will belong to B. X need not belong to S. Okay. But I think it's better because the students are confused that where they will get X and that. It's better to take this because most of the cases it happens. But Wheeler has taken, he has not taken anything. He said any family of subsets of X will form a base, form a sub-base. That means if you take finite intersections of that, that will give a base for a topology. Because he was using this thing. That's why I mentioned here. Remark. In the remark you see that usually sub-base. Okay, but it's better if we take this thing, and because usually it happens. Like, look here. So the remark you should read carefully. Look in R. If you take this thing, for the usual topology given by the on R, the usual distance matrix topology. This won't be a base, but this will be a sub base. Reason is A, B, you can take A less than B as intersections of this. That is giving you that. So this is a sub base for the topology, usual topology and that. Okay, right? I have given the remark. You should read the remark on that. So why some people do not take. If you use Euler definition, X won't be a member of the X minor X. Look here also. I should tell you that. I am not saying X is a member of that. I am only putting this condition. But if you follow Euler definition, X will be in the base. I'm sorry that X need not be in S. I'm all saying putting the condition. Sometimes X is in S because here look, I am getting this R equal to all this union of all this, but R itself is not there. Okay, because R means this thing. This is not there. So that what I think I said something here. So I'm not very sure. But I'm saying that the definition I have picked up, that is from Conway, that sub-base, what I have given here. Here I am putting this condition. X need not belong to S. If X belongs to S, then I don't need to put this condition. It will be automatically satisfied. Okay. But I have taken any arbitrary collection, but only I am putting this condition. Okay. And whereas Willard has not taken this condition at all, without this condition. But he is without this condition because he is taking that thing of the logic from the logic, so that he, in his case, X will belong to the base generated by S. Okay. Also, you should know whatever definition you take, you have this. Okay. In the remember of the when a sub-collection of X, a family subsets of X, when a family of subsets of X form a base, we have this condition. Just because in order to ensure Conway is using this, because Conway doesn't go by that, he's not requiring that action of logic. Okay, so we should be careful that we learn the definition where subbase is giving his X should be in a basic of pencil. Whereas conveys it need not be, but still ultimately it will give you the same topology. Okay, so that you should be careful of that. But in our case, it happens, the condition I put, this happens almost everywhere. It will be very difficult for you to find a case where you don't have it. Okay. Now you see that. Now we would like to see that okay, I'm just coming back. Oh. Well, let me tell you, this condition is given to immediately find out that your condition for a base is satisfied. Okay, but otherwise you'll have to use that axiom of logic and that. At finite, that automatically X will belong here. So Conway didn't want to use that. Okay, that's why he gave this. Okay, now look, it is very convenient that if you have to start with any family, you have this, then that will give a topology. Now, look how this is particularly useful. Actually, that is the only way to define the product topology and arbitrary collection of topological spaces. So that here, now look that base I was taking when you have only finitely many this. Remember that I have taken this collection U1 plus U2 plus UN y plus 2 tau y this is your base. But the point is that first look what does it mean here, so called here the points will look like this xi, okay, like Euclidean space will do that. So that means your first coordinate x1 is coming from here, x2 is coming from here, that's the restriction, xn is coming from here. Okay, right? Got it. Now look, U1 Now look U1. Just look U1. Suppose I have only restriction of a point here. You have this, all these points. Suppose I want to consider all the points in X, the product space. The only restriction I give that I take from particular set, subset of X1, and here is no restriction. That means, look, what does it mean? Then they look this set. So it looks like exactly of this collection of points. Only this is coming from U1, and here is no restriction because it come any point from X2 or similarly from any point of X. So this you have. But if you have this, now look. On the other hand, I have these projections phi 1. Okay. Phi 1 X2 means now look, if I take phi 1 inverse U1, U1 is a subset of X1. I am trying to explain that. Why we go for that definition in the arbitrary cases. U1. Look, it will have all these points, but only the starting from the second coordinate, there can be anything like this. So phi 1 inverse will be exactly this. Phi 1 inverse. Okay. Similarly, you take phi 2 inverse U2, that will give you this thing X1 cross U2 cross X7. Okay. Now look why I am doing it. Okay. Listen is, if I have this now, look here. U1 cross U2 U1. The first coordinate is coming from U1, second coordinate coming from U2, similarly nth coordinate coming from U1. Now look, here, this is the condition. That means when I want to have all the things simultaneously, that means it has to be intersection. Intersection means that exactly. It has to happen for everybody. Whereas union, it has to happen for only one of them. So this means first coordinate will have to come from this. So I take that means, look here, I can write this thing this way. Okay, I can write this way. Look, what I am taking intersection, because all these are members of this. I'm trying to explain that the idea why we'll take that kind of thing for some reason. Now look, you have this obviously because this tells you your first coordinate, other coordinate do not have any restriction. Only first coordinate will have to come U1. But next thing you are doing it, your second coordinate will have to come from U2. That is intersection with it. That means first coordinate will have to come from U1, second coordinate comes from U2. Now you have taken intersection up to this. That means it exactly have to happen. First coordinate must come from U1, second coordinate come from U2, and this way nth coordinate will come from UN. Okay, that exactly I have written everything. I have written everything. Yes, I have taken G instead of U. Okay, so that proposition 3 I have said that the topology, that how you get that projections, how to give them This is a that we have done that. Is a topology and that. That we say the product topology. That I have already defined, proposition 3. Okay. But here I was giving this something. Okay. Proposition 3 already I proved before. That's the motivation, my motivation. And now I am explaining that what does it mean. Now look here. Look here. This one. So this is same as that's it. Okay. So that means what you are getting? Look, it is a finite intersection of the family. That means if I take this phi I inverse Ui, Ui belongs to tau I, 1I less than equal to n, is a subbase for the product topology on this. Look, I am taking this. But this family I could take for any arbitrary thing. Only thing I will do this. So I can take it as a definition for arbitrary product. That means if I take this, now you see that. Suppose I have taken this. I belongs to I. I is arbitrary. This is arbitrary. Maybe finite, maybe infinite. Then on this, I will give a topology that is called the product topology. What? For the product topology, I will take this as a subbase. Like this. But here, this I'll have to write this. I won't say one I running from 1 to n. I is run from all these things. So this will obviously that condition convey has taken that this will be union of this. Union of all this will give you these things. Okay, that you can easily see that. All you need to take, you pick up any point, you show it is here. You can show that. So that's not a problem. Okay. So that this will be a subbase for a topology. On the product space. This is called the product topology. Look, this is consistent with what we have for finite case. Product topology. Product topology, say it is inconvenient. It is not inconvenient. Product topology you should figure out. You always basically you have to handle through this subbase. This will be a subbase. That means finite intersection will be a basic open set. That means projections. Projections play a big role. You basically product topology you always handle through these projections. Okay, but it is not inconvenient, but rather it is very convenient. Only thing you have to remember these familiar projections and this thing will be a subbase. The projections also give you some sort of idea of the geometry. That is also projections. These projections are very important. This is related to geometry also. So that once you have got it, okay. So this is the definition of the product topology. Okay, so let me write that. So that what I'm saying, product topology. You have A family of topological spaces. Of course, I not equal to 5. Arbitrary family of topological spaces. So, on this product space, and product space is non-empty, for that you need action of choice. Okay, since each of them is non-empty, I am taking I is non-empty, by action of choice this will be non-empty. The product topology. I am defining this, taking this. Y is an open set in Xi. This collection, look, these are all subsets of X. This product space, okay, is a subbase of the product topology. Now on this, and you should remember the projections by K xk. If you write this as a point, each function actually is a function, so it goes xkth coordinate. This is all you need to remember. Now the thing that what is Tychonoff's product theorem? I'm not. I have given the proof by assuming Alexander subbase theorem. Okay. So what is the product topology? You have got it. Now what is Tychonoff's product theorem? This is famous theorem. This is a very powerful result in mathematics, in any branch of mathematics. This result says, of course, you have a family of topological spaces. I belongs to I, product topology. Is compact if and only if each xi tau y is compact. Look, this way is easy because you remember that if you have continuous image of a compact space is compact. So if you have continuous onto hello, you see that if you have continuous image, if this is compact, then this is also compact. This is also compact. That means continuous image of a compact space is compact. Now look here, for this each xk. Xk is the each projection, like the thing that the way it has been defined, I should have mentioned that each pi k is open and continuous. The way you did for finite family, that same proof is open and continuous. Is open and continuous. That's the good advantage for the projections. They are good maths, open and continuous. So that if you have this, so that xk, if suppose this is compact, that means pi k of this will be xk. That means xk will be a continuous image of the compact space of this. So xk will be compact. So this is follows from this result. Okay. The thing is that so Alexander's product theorem, the importance is in this direction. In this direction. This is a bit difficult. That Willard, apparently if you look from Willard, he has given proof in 2 lines. But he himself commented after that. He has a para for the comment that Tikhonov didn't have the advantage the time he did. I think 1937 he did that. He didn't have the advantage of these tools. Those are not started there like filter. Okay, even Nate that way it comes the presentive study that came much later. Okay, though Mood Smith convergence came before that. So that the Tikhonov didn't have the advantage and access to all these tools. So, but again, then you'll have to study the filter everything. But but only he used it. But his proof was a bit different. But then this is the Alexander subbase theorem. If you use that Alexander subbase theorem, we don't need to study any Nate or filter on that. What Alexander subbase theorem says. If you use this Alexander subbase theorem, then Tikhonov's product theorem becomes easier. Also, he didn't have access to this. His proof was different. Alexander subbase gave his theorem, I think 2-3 years after Tikhonov's product theorem came. So, what is Alexander subbase theorem? Okay, so this is the question that what is this? Now, by using Alexander subbase theorem, it can be easily proved. That I have given the proof that. Okay. So definition 2, the physical definition of the product topology. Okay. Here basically I was giving the definition of the product topology. Theorem 5. Look at theorem 5. I just want to finish it today. Theorem 5. Tikhonov's product theorem. If and only that he used. Here we have used Alexander subbase theorem. Now look in here before theorem 5 I have given Alexander subbase theorem. Now look, what is Alexander subbase theorem? Now look, if a space is compact, suppose this is compact. Okay. And then every open cover has a finite subcover. It doesn't matter that open set comes from where. That means if you take covered by basic open sets, and if it is compact, then any covered by basic open set will have a finite subcover. Similarly, remember that subbase is actually a subset of this. So any subbasic, this is called subbasic open set. Subbasic open set. Any subbasic open set is a basic open set. Similarly, if you have covered by a subbasic open set, suppose you start with a compact space, then if I have a cover by subbasic open set, so it will have a finite subcover. Now, what is the importance of Alexander subbase theorem? Alexander subbase theorem says this is also sufficient. That means if it happens, every cover by subbasic open set, if and only every cover by sets from S, look, what I say is topological space has be a subbase for the topology tau on X. Then X tau is compact if and only every cover by sets from S has finite subcover. So if you take is the subbase for that tau, and every cover by members of this, see, if suppose every cover, I am not saying every open cover, only every subbasic open cover. Basically, you can say that you can write this way. Every subbasic open cover has a finite subcover. I am not saying every open cover. I am only saying this thing. The Alexander subbase theorem exactly says that if you have this, then it has to be compact. It has to be compact. Now look, I am going to use for Tikhonov's product theorem because on that subbase I am giving that. Now look, I have not given the proof of Alexander subbase theorem, but you can see this is not difficult, but I don't have time. That's why I won't give it. That the Conway you can find. This is a simple proof of that. That Alexander subbasic theorem. Conway's book that a course in point set topology. He's a functionalist. He's an operator theorist, but he also wrote this book. It's a nice book, short book, but it's a nice book. So that now look here in the product topology, I have this is a subbase. This is a subbase for the product topology. So actually for the Pythagoras product theorem, we will show that every covered by this has a finite subcover. And that actually is simple because that gives you the definition of the product topology. Use the definition of product topology. Okay, so that exactly I mentioned that. So now is simple than that. That okay, you'll have to do something, but you can see the idea is that why it will have a any subbasic open cover will have a finite subcover because that finite thing, because finite intersection of all these members will give you the base for the product topology. That actually you use it. Okay, and that I have given the proof. Make sure you read the proof of this. I can may give in the exam that you may use Alexander subbase theorem. By using the Alexander subbase theorem, prove this. Okay. I have, since I have the in-class exam, going to have the in-class exam, offline exam, I have the advantage. I can give some straight question. Okay, so that make sure that you read the proof of this, page 8. You do that. Okay. Now let me tell you that I finished this. So that I taken off product theorem. Make sure Tychonoff's product theorem. You must know its proof. We are allowed to use Alexander subbase theorem. Okay, so this I have finished compactness. I have now from Friday I will teach you connectedness. I will teach you connectedness. I have already, let me tell you that. Last semester I teach connectedness for the metric space, but actually general definition for connectedness, the results proof of that for metric space and topological space there is no much difference. Metric space and topological space, not much difference. So that what I have uploaded, that is the previous semester's note. Only I deleted, I submitted, I replaced metric by topological space. But I will put 2 more notes. Don't think it is over and that. You can upload. I will upload 2 more notes because this thing, so that you make sure that you read the notes before coming to the class on Friday and that. Okay. I will put a questions on connectedness on. With connectedness that I have, I think, briefly mentioned that path connectedness that I want to teach, path connectedness. And there is another kind of connectedness that people usually don't teach much, that is called polygonal connectedness. That you have done, assumed in functions of several variables, polygonal connectedness. Okay, so these notes I will upload later. So Friday I will start from here. Okay, see you on Friday. Bye.